So let's say we have this vector space that we're going to call U, the universe. And that vector space might be like R3, or it might be R5, or it might be just R2, the XY plane, or it doesn't even have to be R anything. It could be something else, like maybe the set of all polynomials. That counts as a vector space. Or the set of all sinusoidal functions counts as a vector space. But just in general, the set of all something, as long as it counts as a vector space. To be a vector space, it has to follow a whole bunch of rules. A vector space just means a collection of things, which we're calling vectors, but which don't necessarily have to look like classical vectors, as long as it follows a bunch of rules. And those rules, we're not really going to get into those rules in a lot of detail, because for our purposes, the main ones that matter are the ones where you can check, is a subset also going to count as a space? If you've got some smaller collection of things within that universe, does that smaller collection of things also count as a vector space? And for our purposes, the only ones you really need to check are closure under addition and closure under scalar multiplication. Because a vector space has to have addition defined. You have to be able to add two vectors together and get another vector. And it has to have scalar multiplication defined. You have to be able to multiply a vector by any real number and get another vector, specifically another vector in that same space. So if you want to check, does S count as a space? And that sense it would be a space contained within some larger space, we would say S is a subspace of universe U. To check that, you just need to check closure under addition. If you take two things in S and add them together, is the result also in S? So if for any, let's say any vector X and any vector Y that are members of set S, X plus Y is in S also. And for any vector X in the set and any real number R times X is also a member of that set. If those two things are true, if adding together two vectors in set S results in a new vector that's also in set S, and multiplying any vector in set S times any real number results in a new vector that's also in set S, then we say that S is a space. And specifically, we would say S is a subspace of U. In this context, sub just means contained within. Like a subset is a set contained within some larger set. A subspace is a space contained within some larger space. In other words, it's a collection of vectors that follows the appropriate rules. But these are the only ones we actually need to check. If these two are true, and it's contained within some larger universe that we already know is a vector space, then we can guarantee that all the other rules are followed as well. So these are the only ones you need to check. It's useful, one of the things that's useful to check first though, what's one vector that has to be a member of every vector space? Which vector is required? Yeah, the zero vector. Part of the definition of a vector space is that it has to contain a zero vector. And that doesn't necessarily mean a column full of zeros like usual. It just means a vector that when you add it to any other vector, doesn't change it. And usually that means a column full of zeros, but it doesn't have to. The important thing about the thing we're calling the zero vector is that it's the additive identity. When you add it to something, it doesn't change the thing you're adding it to. So it's a good idea to check that first. Every vector space has to include a zero vector. So if you want to check, does S count as a subspace, it's a good idea to check first, does it contain the zero vector? If it doesn't contain the zero vector, then you know it's not a subspace and you're done. If it does contain the zero vector, it might or might not be a subspace. You still need to check the closure properties. But it's a good thing to check first because it's very quick to do. You just check, does the zero vector count as this set, part of this set or not? And if it doesn't contain the zero vector, you've immediately ruled out that possibility. You know that it's not a vector space. So this is often a quick way to rule out possibilities ahead of time before you even check the closure properties. Any questions on these terminologies so far? Then let's try this out with an example. Let's say our universe is R3. And let's say we're looking at a smaller set of the vectors in R3. Let's say we have a subset of R3. S is a subset of R3. And let's assume that it is defined by, and we can write this in set builder notation. We're looking at the set of, in this case, all vectors x, 0, 0. So S we're defining as the set of all vectors x, 0, 0, such that x is a member of R, just R. So set builder notation, you list it in curly brackets to say this is a set. The first thing you list is just the general format of what sort of things are in the set. Then a bar that represents such that, and then the properties that have to be true in order to really count as a member of the set. So we're basically just looking at the collection of all 3x1 vectors such that the second and third components are zeros, but the first component could be any real number. And we want to know, does this set of vectors count as a vector space? We know it's contained within R3 because R3 is anything, anything, anything. So we really just need to check the closure properties. If those are true, then we know it's a subspace because R3 is known to be a vector space. First thing though, I would recommend checking, does the 0 vector count as a member of the set? We want to know, is the 0 vector a member of set S? So let's check. If we write out the 0 vector of this universe, the 0 vector is just 0, 0, 0. Does that count as a member of set S? Yeah, it fits this format. The format of set S is all 3x1 vectors such that the second and third components are 0, but the first component could be anything. This is a vector where the second and third components are 0, and the first component is just some real number. It's just that it's specifically the first component is 0. So yes, the 0 vector is a member of set S. And that alone doesn't tell us anything. If the 0 vector was not a member of set S, we would immediately know S is not a vector space. Since the 0 vector is a member of set S, that just doesn't rule it out yet. We still need to check the closure properties. So let's check the closure properties. Let's say, suppose we have two vectors that are both members of set S. Let's say vector U and vector V are both members of set S. Then the only thing we know about vector U and vector V is that they have 0 in the second and third components, but they could have any real numbers in the first component. So we could write those out. We could say U has to be something 0, 0. Let's just make up a variable. Let's say A 0, 0. And V equals something else 0, 0 for some real numbers A and B. Some A and B that are members of the real numbers. We want to check if we add U and V together, is the result still a member of set S? We want to know, is U plus V also a member of set S? So let's check. Let's try adding those together. U plus V would be A 0, 0 plus B 0, 0. And we can just add these one component at a time. Add the first components, A plus B. Second components, 0 plus 0. Third component, 0 plus 0. Does this look like a member of set S? Does it match the requirement that the second and third components be 0, but the first one could be any real number? Yeah, this matches this description precisely. The first component is some real number, doesn't matter which one. The second and third components are both 0. So yes, this is a member of set S. So we've just proven that if U and V are both members of set S, then their sum, U plus V, is also a member of set S, guaranteed, no matter what U and V were. Because we weren't even using specific examples. We were saying U and V could have been any members of set S, and we guarantee that their sum has to be a member of set S as a result. So this proves that yes, set S is closed under addition. We can say set S is closed under addition. And closed here just means you can't leave the set using this operation. You cannot take two things that are members of the set, add them together, and get something outside the set. The result is also a member of the set. So we've shown it's closed under addition. What else do we need to prove in order to guarantee that this really is a space? Yeah, we also need to show that it's closed under scalar multiplication. That if we take some vector that's a member of the set and multiply it by some scalar, some real number, then the result is also a member of the set. And we can keep some of the work we've done here, at least some of the setup. We just need one vector, though, and one scalar. So let's say U is a member of set S. And let's say R is some real number. Then U has got to be a vector that looks like something 0, 0, where A is just some real number. And let's try multiplying them out. We've established an arbitrary vector in set S where the only thing we know about it is that it follows this format. And we've established an arbitrary real number. It could be any real number. We want to know, is it true that scalar R times vector U is also a member of set S? And as before, we check that by just multiplying it out. R times U looks like R times A 0, 0. And if we actually multiply that, we can just multiply the scalar by each component, just based on the usual rules of multiplying a vector by a scalar. So we get R times A, 0, 0. Does that fit the format of a real number 0, 0? Yeah, R and A are both real numbers by our original assumption. So R times A real number times a real number, is guaranteed to also be a real number. So yes, this fits the format. So R times vector U is also a member of set S. So we've just shown that if R is any real number, any scalar, and U is any vector in set S, then the result of multiplying scalar R times vector U is guaranteed to also be a member of set S. So we've just proven that set S is closed under multiplication. Since we've showed both of those properties are true, and also S is a member, or S is a subset of something we already know as a vector space, then those pieces of information are enough to prove that S is a vector space in its own right. And since S is a vector space that's enclosed within some larger vector space, we would say S is a subspace of R3. Any questions on that so far? And moreover, now that we've shown that this is a vector space, we should be able to find a basis for it, because any vector space should have a basis. In other words, a small collection, ideally small collection of vectors. It might end up being very large, but in this case, R3 is only 3-dimensional, so any subspace is going to be no more than 3-dimensional. We should be able to find a set of 3 or fewer vectors that spans all of set S. And one way to do that is to just write out the type of vector that shows up in set S as arbitrarily as possible. So to establish a basis, let's say U is some vector in set S. Then all we know about vector U is that it's something 0, 0. So let's just write it that same way, A, 0, 0, with A being some arbitrary real number. Since we've got A in, I guess you could say every term here, even though it's really just one term, we can factor A out of that. If we factor out that free variable A, then what's left? Yeah, 1, 0, 0. And again, since U could have been any vector in set S, that means that every vector in set S can be written as 1, 0, 0 times some scalar or other. Anything 0, 0 can be written as 1, 0, 0 times some multiplier, which means that this vector 1, 0, 0 is a basis for set S. We can say that instead of writing S as set builder notation, we can say S is the span of that one vector, 1, 0, 0. And since we only need one vector to span the set, we would say that set S, or subspace S, is a one-dimensional subspace. Specifically, we'd say S is a one-dimensional subspace of a three-dimensional universe. And we would call S one-dimensional because a basis for S only has one vector in it. In fact, what is set S? What do you call the collection of all points in XYZ space that have any X coordinate, but the Y and Z coordinates are both 0? What region of XYZ space are you looking at there? If you were to map that out, if you just had, let's say, Y-axis, Z-axis, and X-axis coming out of the board, what region are we talking about when we're describing all of these points, like points in space, where the X coordinate could be anything, but the Y and Z coordinates are both 0? What region of space are we talking about there? Yeah, that's just the X-axis. We're looking at all the points on the X-axis itself. And of course, going backwards as well. So set S is just the entire X-axis. And this is one-dimensional in the sense that a straight line is one-dimensional. But in terms of linear algebra, we describe it as one-dimensional because we only need one vector to span it. The entire X-axis consists of multiples of this one vector. So we say the dimension of set S is 1 because we only need one vector to span it. Any questions on that so far? All right, let's try out one more example in a similar sort of style. Let's say we instead define set X or set S as the set of all vectors X, Y, Z, such that Z equals, let's say, X minus 2Y. We would go through the exact same sort of procedure for proving that S is closed under addition and closed under scalar multiplication. It might be convenient to rewrite XYZ as X, Y, X minus 2Y. So for instance, in order to prove that this is closed under scalar multiplication, you'd write out two examples of vectors like this. Not just specific examples, but generic examples using variables. Like you could start with, let's say, A, B, A minus 2B. This is an arbitrary member of set S. And then let's say C, D, C minus 2D. Add those together and show that the result still follows the format of a number, another number, the first number minus 2 times the second number. As long as you can show that this results in something that still follows this rule, where the Z component is the X component minus 2 times the Y component, that means the set is closed under addition. Same thing with scalar multiplication. Just take this vector, multiply by some arbitrary real number r, and show that the result still follows this rule. So try that on your own just to get some practice with that. You should end up with finding that this is closed under addition and multiplication. But given that this is a subspace of R3, let's try writing out a basis for it. If we say let U equal a vector that looks like that, let's say A, B, A minus 2B as a member of set S. This is a truly arbitrary member of set S. Since A and B could be any values, that means that this could be any vector in set S. And how many free variables do we have here? How many, if we wanted to create one specific vector, how many choices would we be making? How many variables would we need to choose values for? Yeah, we need to choose values for 2 variables. We choose a value for A, choose a value for B. In fact, we could even list out some examples. For instance, you could say let A and B both be 0. Then you get 0, 0, 0. So the 0 vector is a member of set S, which it better be, because if it's not, then that's not a subspace. Or let's say we set A equal to 1 and B equal to 5. 1, 5, 1 minus 2 times 5 would be negative 9. So 1, 5, negative 9 is another member of set S. Or maybe you set A equal to 10 and B equal to 0. 10, 0, 10 minus 0. So these would all be examples of vectors in set S. But the important thing is to create a vector in set S using this format, you'd have to choose a value for A, choose a value for B, but then the value of A minus 2B is set by what you chose for A and B. So we would say that in this case, we would say X and Y are free variables because you can choose whatever you want for them. But Z would be a fixed variable because its value is determined by the choices you made for X and Y. And the number of free variables indirectly tells you the dimension of the space. Since this format involves 2 free variables, 2 choices we can make, that suggests this should be a 2-dimensional subspace. In other words, we should be able to write it in terms of 2 basis vectors, 1 for each free variable. And the way I would recommend doing this is splitting out your format based on free variable. If we write this as 2 vectors added together, a vector with all the A's and a vector with all the B's. And I'm going to start from the bottom up just because the bottom is the only term that has both A and B. The bottom term could be written as A plus negative 2B. The middle term, we have B but no A. So we could write this as 0A plus 1B. I'm going to go ahead and fill in a 1 on the A also. So the middle term, since it's just B, we could write that as no A plus 1B. And likewise, the top term is just A, so we could write it as 1A plus no B at all. So same vector, just rewritten by splitting it out into the A terms in one vector and the B terms in another vector. And the reason that's useful is that we can now, since the first vector has A's and everything, we can factor out A. Since the second vector has B in every term, we can factor out B. And what's left when we factor out A here? Yeah, 1, 0, 1. And when we factor B out of this one, yeah, 0, 1, negative 2. Which means that every vector in set S, because U could have been any vector in set S, every vector in set S can be written as a linear combination of these 2 vectors, which means S is the span of these 2 vectors, since span just means all possible linear combinations. And we would say these 2 vectors are a basis for set S, a basis for that subspace. So we'd say S is the span of 1, 0, 1, and 0, 1, negative 2. Since we need two vectors to span it, we would say S is two-dimensional. And what would that look like on the graph? If you actually graphed this, what would a two-dimensional region look like? What shape are we creating here? Like if you were to graph this equation, if you were to graph this by hand or punch it into a graphing calculator, yeah, you'd get a plane. Specifically, the plane is z equals x minus 2y. It's the set of all points x, y, z, such that the z coordinate happens to be x minus 2 times y. So that forms a plane. You can tell that geometrically by graphing it, or you can tell that algebraically by decomposing it into basis vectors. And you find that a basis is just two vectors. That means the space is two-dimensional. So in this case, we would say set S is a two-dimensional subspace of a three-dimensional universe. Any other questions on that so far? And this should work for any subspace. Anytime you're trying to find a basis for a subspace, try writing out an arbitrary generic vector in that subspace in terms of variables, using whatever requirements need to be met to count as part of that subspace. Try writing that in as few variables as possible using whatever substitutions you have. Usually the restriction itself can be written as a substitution. Like we can replace the z coordinate with the x coordinate minus 2 times the y coordinate. Identify how many free variables you've got and try splitting that out into vectors added together, one vector for each free variable added up. Then factor the free variable out of each of those vectors, and what's left should be the basis vectors, or a set of basis vectors. There are, of course, other basis vectors. You could take, for instance, 3 times this minus 1 times this, or 10 times this plus 5 times this. That would get you two other vectors you could use as a basis. These are probably just the easiest vectors to use as a basis, but there's infinitely many bases to use. In fact, any two vectors, since this is a two-dimensional subspace, any two independent vectors in this subspace will count as a basis for the subspace. But these are probably going to be the easiest ones to use. Any other questions on that so far? All right, let's try applying this to the idea of a null space of a matrix. Let's say we've got some matrix. I'm not going to worry too much about what it is right now. Let's just say we've got some matrix and we row reduce it all the way to reduced row echelon form. Because if you want to find the null space of a matrix, that's typically your first step. Row reduce it completely. Because you want to find all vectors that, when multiplied by the matrix, give you 0. That's the definition of null space. All vectors x such that a times that vector equals 0. And typically to solve ax equals 0, you write out the augmented matrix A augmented with column of zeros. Row reduce all the way to reduced row echelon form. And then from that, you can read off the answers, or at least read off equations that can be used to make the answers. So let's say you row reduce matrix A and you find that the result looks something like something like this. So you augment A in the 0 vector, and you row reduce it all the way to reduced row echelon form. So every pivot is a 1 and alone in its column, 1 and alone in its column, 1 and alone in its column, 1 and alone in its column. And let's say we now want to turn this row reduced echelon form into a basis for the null space. We want to find all vectors that fit the null space. What we can do is rewrite each of those rows as an equation. Let's say, since this is 1, 2, 3, 4, 5, 6 variables, so x is going to be a 6 by 1 vector. Let's say vector x is A, B, C, D, E, F. So that means each one of these columns can be treated as the coefficient of one of those variables. Coefficients of A, coefficients of B, C, D, E, and F. So we should be able to rewrite each one of these rows as an equation. For example, the first row, what would the first row look like as an equation? Yeah, we've got 1A, no B at all, 3C, no D, 2E, and no F. So we can say that 1A plus 3C plus 2E equals 0. And then what about the second row? Yeah, B minus 2C plus 2E equals 0. And then third row, yeah, 1D plus 5E equals 0. And fourth row, yeah, F equals 0. And then in some cases, there might be another row. Maybe there's a row that's all zeros. If there's a row that's all zeros, that doesn't really give you any new information because it just turns into 0 equals 0. And we already know 0 equals 0. So you want to focus on the rows that actually provide information. Each one of these rows, when reduced, provides restrictions on what the values of the variables can be in the simplest possible format. And what we can do then is we can turn this into more useful information about this vector by solving for each of the fixed variables in terms of the free variables. For instance, in this first equation, what would be the easiest variable to solve for? If you wanted to just isolate one of those variables, what would be the easiest variable to isolate? Yeah, let's try isolating A.
Hello.
You just subtract 3C from both sides, subtract 2E from both sides. A equals negative 3C plus negative 2E. And likewise, in this equation, what would be the easiest variable to solve for? Yeah, isolate B by just adding 2C to both sides, subtracting 2E from both sides. And in this one, we'd probably want to solve for, yeah, D equals, just subtract 5E from both sides, negative 5E. And then F equals 0. We don't even need to solve for anything. It's already isolated. So why is it that those were the easiest to solve for? Why was it easiest to solve for A and B and D instead of, for instance, solving for C or solving for E? What's special about variable A in this equation that made it easy to solve for? Like, why was it preferable to solve for A instead of solving for C or solving for E? Well, why do we consider those to be free variables? Why do we choose C and E to be free variables instead of choosing A to be the free variable? Algebraically, why is it easiest to solve for A? What's special about the variable A in this equation that makes it easy to solve for? Or let me put it another way. What doesn't A have attached to it? Yeah, It doesn't have these messy coefficients. The coefficient on A is 1, so that makes it easy to solve for. Coefficient on B is 1, so that makes it easy to solve for. Coefficient on D is 1, that makes it easy to solve for. And also, A only shows up in this one equation. We can isolate A in this equation and not have to worry about showing up in the other equations. Whereas C shows up in several equations, E shows up in several equations. So that would make it more complicated to solve for. So those are really the key attributes of these variables that we're solving for. We're choosing to solve for the variables that have 1 as the coefficient and that only show up in one equation. In the reduced row echelon form, that corresponds to a value that is 1 and only shows up in that row. A value that is 1 and doesn't show up in any of the other rows. A value that's 1 doesn't show up in any of the other rows. And a value that's 1 and doesn't show up in any of the other rows. This is the whole idea of reduced row echelon form in the first place. The reason why reduced row echelon form requires each pivot to be a 1 and alone in its column is such that each fixed variable in the equations only shows up in one equation and has a coefficient of 1. The whole point of reduced row echelon form in the first place is so that when you rewrite that as equations, some of the variables are going to be incredibly easy to solve for. And those are specifically the variables that show up as pivots. So in general, in row reduced echelon form, any column with a pivot corresponds to the fixed variables. A, B, D, and F are the fixed variables here, specifically because those are the columns with pivots. And then the columns without pivots, so variables C and E, those are going to be the free variables. So you solve for each of the fixed variables in terms of the free variables. So columns without pivots turn into free variables. Columns with pivots are going to represent fixed variables. And have you seen the term rank yet? The rank of a matrix? Has that shown up in class at all? Some yes, some no. In general, the rank of a matrix is just the number of pivots in the fully reduced row echelon form. So you've got it completely to reduced row echelon form. We have 4 pivots. So the rank of the matrix is 4. And that also corresponds to the number of fixed variables, because each of the fixed variables is just a variable from one of the columns that has a pivot. So each pivot tells, or the number of pivots in the final reduced row echelon form tells you the rank of the matrix. And that's also the number of fixed variables in the equations. Whereas the number of free variables is called the nullity. The nullity of A, usually just abbreviated as null A, but that means the nullity. The nullity is the number of free variables, which in this case would be 2. And since the rank is how many columns that have pivots, and the nullity is the number of columns that don't have pivots, when you add those up, you just get the number of columns. Rank plus nullity is 6 because there are 6 columns in this matrix. With that, let's try also solving for A, B, C, D, E, F. We can make some substitutions here. We know that A is negative 3C minus 2E. So I'm just going to replace A with negative 3C minus 2E. We know B can be rewritten as 2C minus 2E. C is a free variable, though. C could be anything, so I'm just going to leave it as C. We also know D can be rewritten as negative 5E. E is a free variable, so I'm just going to leave E as itself. And we also know F has to be 0, so I am going to write in 0 for F. So we've taken a vector that has 6 unknown variables and reduced it to a vector that has only 2 unknown variables, because those are the 2 free variables. 2 free variables also suggests the null space is going to be 2-dimensional, which is another interpretation of nullity. The nullity is the dimension of the null space. two free variables means a two-dimensional null space. So we say the nullity is 2. And with this written in terms of only two free variables, we can split this up into two vectors. So let's try that out as well. We can write this as a C vector plus an E vector. So the first term, negative 3C plus negative 2E, negative 3C plus negative 2E. Second term, 2C plus negative 2E. Third term is just C, so I'll write that as 1C plus 0E. Fourth term, negative 5E, so that's no C plus negative 5E. Fifth term, no C at all, but 1E. And I'll need a little more space down here. And final term, no C and no E, because it's just 0. So 0C, 0E. So this is the general solution vector split out into a C column and an E column. And we can also now factor out C and factor out E. Because this first vector, you factor out C, you're left with negative 3, 2, 1, 0, 0, 0. And the next one, factor out E, you're left with negative 2, negative 2, 0, negative 5, 1, 0. That means every vector in the null space, every solution to AX equals 0, can be written as a linear combination of negative 3, 2, 1, 0, 0, 0, and negative 2, negative 2, 0, negative 5, 1, 0. So these two vectors form a basis for the null space. We can say the null space equals the span of this vector and this vector without the coefficients. So this is a very useful way of finding a basis for the null space. And since there's only two vectors in the basis, the nullity is 2, we would say the null space of this matrix is a two-dimensional subspace of a six-dimensional universe, because there's 6 terms in each of these vectors. So a two-dimensional subspace of a six-dimensional universe, that's the null space. Any questions on that? All right, try this out on your own, get some practice with other matrices. You can really just take any matrix you want and find the null space using this method. Row reduce it completely to row reduced row echelon form, rewrite each row as an equation, and then you can solve each equation for the one and only one fixed variable that shows up in it. Fixed variables being the ones that are the ones whose columns have pivots. So solve for each fixed variable in terms of the free variables, make those substitutions in the general solution. So you should be able to write out the general solution in terms of as many unknowns as you have free variables. Split it out into a vector for each free variable, factor out the free variables, and whatever is left should form a basis for the null space. So give that a try. Let me know if you have any questions, and I will see you next time. You're welcome.